And if you can turn to the next section of notes, which is gas stoichiometry. All right, for those of you at home, here's the answer key to the homework from last night. You can just pause the video, get your, check your work. I went through this already with the folks that were here, and then I forgot to record this, so that's why I'm just doing this, but I'm going to do it kind of quickly. So you might need to pause the video to get all of the answers. All right, so moving on, we are going to move over to our notes here. Maybe, there we go. Okay, so we're going to start a section called gas stoichiometry. This is going to take stoichiometry from chapter 11 and combine it with our ideal gas law from this chapter. So you remember how we use gas stoichiometry, how we used stoichiometry where we had our clouds and that sort of thing. We also have Avogadro's principle that says that if we're at STP, we have equal numbers of particles. So we're going to use that principle for part of this today as well. Avogadro's principle only works at STP, so we have situations where we're not at STP. We've got to use the ideal gas law and then use stoichiometry to solve our problems. Okay? So if we have volume to volume here, we're going to start with a balanced equation. So for this guy, we would have oxygen gas is needed for the complete combustion of propane. So this is a combustion reaction. So C3H8 plus O2. Is this in your notes? Do you have this problem in your notes? You see where I'm at?
I don't know. I don't have them.
I gave you the packet.
That's what that was?
Yeah.
Oh, I thought it was the homework. It's both. Oh, it's both? I thought it was just the homework, that's why. Yeah, I put it in here. No.
That's the one.
No, that's the one.
So it's probably close by, I'm guessing.
This one.
Yeah.
There we go.
And the notes are in the front, and then the homework is in the back.
Okay. Thank you.
Or maybe I did do it every other one for you guys. I can't remember anymore. No, there's gas right now. That's the problem that we're on right now.
I think. Does that look right?
Yeah.
Okay. All right, we're back. All right, so combustion reaction, we have oxygen, we've got CO2, we have water here. And this guy, when we're doing this, we are using our stoichiometry, so we've got to balance our equation. Remember, if our carbon is odd, we just go ahead and start balancing our carbons. We balance our hydrogens, and then we go back and balance our oxygen. So I've got 6 oxygen and 4 is 10. So there's my balanced equation for this guy. All right. So now, when we were doing our regular stoichiometry, I gave you a rule. And I said only moles in the holes. Do you remember that? Well, we can have something else in the holes too. We can have volume in the holes now. So we can have, since we've got volume here, we can actually put volume in the holes. They're telling us that we have 4 liters of this. So we just run this the same way we would regular stoich, except instead of moles in the holes, we can have liters in the holes now. Okay. So I'm going to have 4 here. If I had 4 here, they're asking me what volume of oxygen would I need. So I'm going to take this 4. 4 is going to become my cloud because it's divided by 1, and then I multiply by 5, that means that I'm going to need 20 liters of oxygen. Okay. All right. So what volume of oxygen is needed to react with solid sulfur to form 3.5 liters of sulfur dioxide? So we've got sulfur plus oxygen is going to give us sulfur dioxide. Okay. This is my before, my change, and my after table here. I don't draw tables as nice as Microsoft Word. Okay, we're going liters to liters. So liters to liters, I can put liters in here. So I want to produce 3.5 liters of this. Okay, that means that I'm going to have to start out with how many liters of oxygen? What would have been in my cloud up here? 3.5, because this divided by 1 is 3.5, which means when I bring it down and I multiply by 5, that's going to be 3.5 here as well. Okay, everybody cool? All right, see if you can do the next one. We're forming water. Remember the formula for this is H2 plus O2 yields 2H2O. See if you can figure out. We're starting out with 5 liters of this. Figure out how many liters of that we would need. Yep, 10.
Right?
Yeah,
Okay.
because you divide this by 1, your cloud becomes 5 then. Then you pull this down, that's going to be 10 liters. Too easy? Yeah. Yeah. All right, this is the same equation from up above, so you guys can copy that one down if you want. It's C3H8 plus 5O2 yields 3CO2 plus 4H2O. Okay, how many liters of propane? So we're figuring this out, and this is 34 here. And this is a 5. Didn't come through real well on here. It's kind of a problem when you write one spot and your writing shows up in a different spot. It's a little hard to do. Yeah.
So for the O, is that an S or a 5?
Can you say what? What?
For in front of oxygen, is that an S or a 5?
It's a 5.
Okay, thank you. Wait, so where the question mark is?
Huh?
From the question mark, the 170?
No, you've got to take this and divide by 5.
Hold on, I multiplied and I.
So 34 divided by 5, I think it's like 6.8.
Yeah, 6.8.
Okay.
6.8 would be what the question mark is.
Yeah.
I just multiplied and divided in the
Yeah.
order. Okay. Sorry.
All right, methane is C4 or CH4. Got ahead of myself. CH4 plus O2 yields CO2 plus 2H2O. And I got to go back here and put a 2. All right. See if you can figure that one out. We're figuring out this. We had 2.36 here. What'd you get?
4.72.
4.72 liters. Very good. Okay. All right. Now, this is where the fun begins. So if we are at STP, we can just use Avogadro's principle. But sometimes we're not at STP. So here, they're asking us for grams. So they're giving us liters of nitrogen, okay? But they want to know grams of ammonia. Since this is not at STP, we can't use Avogadro's principle. So what we're going to have to do first is we're going to have to convert this to liters of ammonia. Okay, and then we have to use the PV equals nRT formula to get the moles and then convert moles to grams. So that is our game plan, so to speak. Okay, so we've got ammonia is being synthesized from hydrogen and this should say and nitrogen gas. Is synthesized from hydrogen and nitrogen gases. So ammonia, this is the formula. So we've got H2 plus N2 yields NH3. Okay, I got to balance this. So I'm going to put a 2 here. That's going to get my nitrogen balanced. And then I'm going to put a 3 here to get my hydrogen balanced. Okay. So my game plan was I was going to convert my liters of nitrogen over to liters of NH3. So I've got 5 here. So that would make how many here? 10. Okay. Now I'm going to use that in my PV equals nRT formula. So remember PV equals nRT. If we're solving for N, okay, this 10 liters is going to be right here. We're solving for N. N is going to equal PV over RT. Everybody cool with that algebra? Good with the algebra?
Yeah.
Okay. This V is coming from right here because we want to talk about ammonia. And we want to solve for grams of ammonia. We're actually going to end up solving for moles of ammonia and convert it. All right, my pressure was given here is 3. My volume we calculated right here as 10. My R value, which R value am I going to use? Remember I had 3 different R values. And the 0.08, 20, or 21. I had the 62.8. You guys have the table there. I don't. 4. Okay. And then I had the 8.314. Okay. When my pressure is given in ATM, this is what I want to use. If my pressure is given in millimeters of mercury, I want to use this one. And if it's given in kilopascals, I want to use this one. So which one of these am I going to use over here? First, the second, or the third? The first one, because my pressure was given in ATM. I want to use the R value that contains ATM in it. The 0.0821. And then I need to multiply my temperature. I need to make sure that it's in Kelvin, which it is. So we're good to go. Okay. So 30 divided by 0.0821 times 298 in parentheses. Put on my glasses so I can read it. I got 1.23 here. And that's going to be moles of NH3. They didn't want moles. They wanted grams. So I need to multiply the 1.23 times the molar mass for this guy, which 1417 is the molar mass for him. So I'm going to multiply him by 17, and I get 20.8 grams. of NH3. Works. All right, the next one's at STP, which makes life easy. Okay, so here we calculate the mass of the solid ammonium nitrate at STP. We can just use Avogadro's number here, or Avogadro's principle, I mean. So this guy, we can just go back and work with the stuff that we were given before. We know that we have 0.1 liters of dinitrogen oxide. Okay. That is right here. I should have this lined up underneath my equation. This is 0.1 liters of this guy. And they want to know the solid ammonium nitrate. So if this is 0.1 liters, the problem is that it only works for gases. But we're at STP, so 0.1 liters. Okay, so we've got my liters here. I want to solve for moles then. So I've got 0.1 liter. My pressure, it's at STP, so I want to use 1 atm because that makes life easier. So this is my PV. Should I have backwards? PV equals nRT. Okay. My pressure, they said I'm at standard temperature and pressure, so my pressure is going to be 1 atm times the 0.1 for this guy, okay, equals, my N is what I'm solving for, R is 0.0821, and my temperature at STP is 273. So 0.1 divided by parentheses, 0.0821 times 273 in parentheses equals, my N value here is going to equal 0.00446 moles of N2O. Okay. Now, my stoichiometry tells me that 0.00446 moles of this guy would mean that I would have started with how many moles of this? What's my cloud here? Right. So then I've got, that means that I multiplied by 1. This guy is going to be 0.00446. Okay. So then if they want to know what mass I need, this is moles. So I need to turn that guy into moles then. So 0.00446 moles of NH4NO3. If I multiply that by the molar mass of NH4NO3, which is 28 and 4 and 48. So I got 80 for the molar mass for that guy. My moles will cancel out. And I can multiply that by that, and I end up with 0.357 grams of NH4NO3. Okay, good. All right, calcium carbonate is forming limestone when it's heated. It decomposes to form calcium oxide gas. So this is a solid here. Forms solid calcium oxide. So this is a solid, and this is a gas. Okay, so how many liters of CO2 will be produced at STP if we start out with this many kilograms of calcium carbonate? So because these are solids, Avogadro's principle only works when everything's gases. So that's why we can't use his principle here and be able to just convert, gases and that sort of thing over. We got to go back to that PV equals nRT formula. All right. Here we're given kilograms of calcium carbonate though. So this is 2.38 kilograms of calcium carbonate. So I need to convert that into moles so I can put it on a BCA table. So first of all, I need to get kilograms out of grams into grams, and then I need to get grams into moles. So see if you can figure out what that value is going to be. All right, so I got 23.78, 23.8 moles, 3 sig figs, so 23.8 moles of this. All right, was this guy balanced? He was. So that means they're asking about carbon dioxide. So that means that I'm going to have the same number of moles of carbon dioxide produced, right? So if I have that many moles of this produced, right, I'm going to put that into my PV equals nRT formula, and I'm solving for V. So see if you can solve for V. This is your N value here. Make sense? You get that value? All right, so see if you can solve for this one. You've got 10.5 liters of this guy. They want to know moles of water vapor. So this is still going to be a gas. So we can use our gas, our stoichiometry here with our moles. Okay. Remember, our cloud's going to end up being 10.5. Then you're going to sub in that value. That's going to be your volume in your PV equals nRT formula. Okay, here's your temperature, but remember you need it in Kelvin.
That's just 5.25.
Here?
No, for like, wait, no. I think for like under the two.
Oh, yeah. When you go up into the cloud would be 10.5, and then you're going to multiply down. So 10.5 times 2, I think, is 21.
Oh, because you're taking, so I'm multiplying it by 2, so it would go.
When you go into the cloud, you divide. When you come out of the cloud, you multiply.
If that makes sense.
All right, so this one you're going to start out with your grams of iron. You're going to convert that into moles, and you'll do a mole-to-mole conversion over into oxygen, and then you use your PV equals nRT to figure out the volume. you do on that one? You did okay? All right, so we got potassium reacting with chlorine gas. They're going to form potassium chloride, so we need to balance this guy. Okay, and we're starting out with 0.204 grams of potassium here. That was solid potassium, so since it's solid potassium, we can't use the Avogadro's principle. We gotta take these grams, we gotta convert them into moles, and then stick that into the PV equals nRT formula. Okay, you have this one done already, Avery? Okay, I'll whip through and get you an answer then. Okay, so I need to figure this out. So 0.204 divided by potassium is 39.1 and 0.00522. So I'm going to divide that by 2 to get this guy. So that's going to be 0.00261. And I'm going to throw that guy into this formula. So I'm solving for volume. So volume is going to equal nRT over P. It's at STP. So this is going to be 273. And I'm going to make my pressure 1 because I used ATMs. So take that times 0.0821 times 273, and I get 0.0585 liters of Cl2. Is that what you got? Okay, perfect. All right, I think that's the end of the notes. We are done with this chapter, you guys. Exciting times. So, I think you have check your packet sitting there. Remember what you have. You've got practice on gas stoichiometry. Yes, the 13.4. And then you've got a review coming up, chapter 12 review, and then chapter 13. Oh, that's right, because I'm combining these chapters, aren't I? Okay, so 13.4 I want done by next class period. We'll check that. I'm going to have you do some demos, or I'm going to do some demos for you next class period. The next time I see you, I want 13.4 done. So I'm going to do demos for the people tomorrow. No, I'll probably, what am I going to do tomorrow? Yeah, I'll probably do demos for them tomorrow, do the demos for you guys, and then have everybody's review due the next time I see you. So that's kind of the way we're sequencing this out. Let me see here if I can erase some of this stuff and kind of figure out our game plan here for the rest of this chapter and next. All right, so let's see here. Game plan. Today is Tuesday. Tuesday we did gas stoich. Wednesday we can do, I can go over the gas stoich, which is 13.4. That's your homework. And go over the answer key for 13.4 tomorrow and do demos with them. they can get the review. The review will then be due on Thursday for chapter 12. Let's do the chapter 12 review for them that night and for you guys. So you'll just work on the chapter 12 review tomorrow in your own time. Thursday, then I will do the demos for you guys so that you can see them. And then your homework will be the review for chapter 13. Friday, we will go over reviews. And Monday, Tuesday of next week will be your chapter 13 and chapter 12 test, depending on which day you're in. Okay, so that's kind of the game plan that we have going forward for the next. So chapter test is either on the 26th or 27th, depending on which day you're here. For you guys, I think that makes that the 27th. I think you're, no, you would be a Monday group then, wouldn't you? So you're around the 26th. And then the people at home, your test will be on the 27th. Okay, so that's the game plan. Any questions about kind of where we're headed here? All right, so homework tonight is 13.4. And for those of you at home, I'll get this video posted and we can go from there.